and welcome to Module 7. In this module, we present an introduction to our Sun, its structure and components. We will also explore the basis of thermonuclear fusion in stars. The volume of our star is so massive, it would take 1,300,000 Earths to fill it. Here is an image showing the Earth's size in comparison with the Sun.
Earth is tiny.
The Sun shines with the blast of 4.5 billion 1 megaton hydrogen bombs every second. 1 megaton equals the explosive power of 1 million tons of TNT. The Hiroshima hydrogen bomb produced the explosive power of 20,000 tons of TNT. It would take 50 simultaneous explosions of Hiroshima-sized bombs to equal the explosive power of 1 megaton. But our Sun shines with a blast of 4.5 billion 1 megaton hydrogen bombs every second. Thus, our Sun's energy output in 1 second is equal to the simultaneously explosive power of about 225 billion Hiroshima-sized hydrogen bombs. The Sun also burns away over 600 million tons of hydrogen from its mass every second. This is an image of the Sun when viewed in the UV wavelength.
Showing the massive energy involved in the photosphere.
Proxima Centauri is a tiny red dwarf class star with only 10% of our Sun's mass and 0.006% of its luminosity. It is incapable of supporting human life and has no planets. It is simply the third member of the Alpha Centauri triple star system. The Alpha Centauri star system consists of 3 stars. The third star, known as Proxima Centauri, Proxima, or Alpha Centauri c, is probably gravitationally associated with Alpha Centauri AB. Proxima is at the slightly smaller distance of 1.29 parsecs, or 4.24 light-years from the Sun, making it the closest star to the Sun, even though it is not visible to the naked eye. The separation of Proxima from Alpha Centauri AB is about 0.06 parsecs, 0.2 light-years, or 13,000 astronomical units, which is equivalent to 400 times the size of Neptune's orbit. Our Sun's surface temperature is 5,800 degrees Kelvin, or 10,000 degrees Fahrenheit. How can that be determined? In this image, you see that as an object heats up, it gets brighter, emitting more electromagnetic radiation, or photons, at all wavelengths. Because our Sun is hot and emits light, astronomers call it a black body radiator.
Yep, if it's a bright object, astronomers call it a black body radiator. This graph shows us that as an object's temperature increases, the relative number of photons emitted changes. And so we see the plots of 3 stars, surface temperatures of 12,000, 6,000, and 3,000. And notice that the maximum peak for the 12,000 degree is beyond visible light, whereas the 6,000 degree body is within the visible light range. So intensity is a measure of how much energy a body emits per second per square foot on its surface.
An ideal black body is a hypothetical object that absorbs all electromagnetic radiation that strikes it. The black body then re-emits the energy it has absorbed, but with different intensities at each wavelength. In human language, a black body is a hot object that emits light. A black body curve depicts electromagnetic radiation emitted as a function of intensity versus wavelength. Wien's law states that the intensities of different emitted radiations reveal a star's temperature. That is, the hotter any object becomes, the shorter its wavelength max, and vice versa. Wien's law proved very useful in calculating the surface temperature of a star, because all we need to know is the dominant wavelength of a star's electromagnetic radiation. We do not need to know the star's size, distance, or any other physical property. Notice how the hotter any object becomes, the shorter its wavelength max, and vice versa.
Shorter wavelength, max.
Photosphere means the sphere of light. It is the visible layer of the sun. This thin region is about 250 miles thick. It has a blackbody spectrum average temperature of 10,000 degrees Fahrenheit. And although we speak of the solar surface, the sun is so hot that it has neither liquid nor solid matter anywhere inside it.
This is critical to remember about stars. Stars are giant thermonuclear fusing balls of gas, hydrogen and helium. There are no solid surfaces in stars. Stars are not solid. They're giant balls of burning gas.
Moving down through the sun, we continually encounter even denser and hotter gases. The center of the sun is 15.7 million degrees Kelvin. The sun appears to have a surface only because most of the visible light comes from this one specific gas layer.
Again, all stars are hydrogen-helium fusion gas balls. There are no solid stars. Stars are gas balls. Very good.
The photosphere is the innermost of the three layers that comprise the sun's atmosphere. Because the upper two layers are transparent to most wavelengths of visible light, we see through them down to the bright yellow photosphere. Here are some facts about the sun's photosphere.
Again, the photosphere is just a 250-mile thick layer of gas that is on the surface of the other gases. And it's called the photosphere.
Review this image for more information about the layers of the solar atmosphere.
Above the photosphere, we look down through the chromosphere and the corona. We only see those with photographic effects.
The limb of our sun is the apparent edge of the sun as seen in the sky. Limb darkening is the phenomenon whereby the sun is darker near its limb than near the center of its disk.
Again, the sun is not changing color. It's the angle and the size that is refracting the light towards the orange instead of the yellow because of the distance.
Using a telescope, we see a blotchy pattern called granulation on the photosphere. The lightly colored granules measure approximately 625 miles across and are convection cells of gas.
So each bubbling gas cell in the photosphere is about the size of the state of Florida and 10,000 degrees temperature.
Immediately above the photosphere is a dim layer of less dense gas called the chromosphere, which means sphere of color. For centuries, this layer was only visible when the photosphere was blocked by a total solar eclipse. The chromosphere layer is approximately 1,500 miles thick. This photograph of the chromosphere was taken during an eclipse. It appears pinkish because the gas in the chromosphere emits only certain colors, among which the reddish-pink one from hydrogen gas dominates. The chromosphere is characterized by the appearance of spicules and supergranules. Spicules are spikes of jets of gas. They rise at 45,000 miles an hour and reach heights of 6,000 miles. then collapse and fade away. Supergranules are enormous regions of rising and falling chromospheric gas. A typical supergranule has a diameter slightly larger than the Earth.
Did you hear that? Each of the supergranules you're looking at is a region larger than the entire planet Earth. It's a bubble of gas.
The corona is the outermost region of our Sun's atmosphere. It extends several million miles out in space from the top of the chromosphere. This X-ray image of the Sun's corona, taken in 1999, provides hints of the complex activity taking place on and in the Sun. The million-degree gases in the corona emit the X-rays visible here. The outflow of gases from the Sun prevents most of the gases from flowing in space and prevents other stars from entering our solar system.
So here in the center is our solar system. We see where the Voyager spacecraft have traveled, and we see the shock wave from the solar wind. The solar wind, called the heliosphere, prevents excess UV and X radiation from entering the inner solar system and frying us.
Some of the gas in the corona is moving fast enough to escape our Sun's gravitational field forever and race into space. This gas travels at about 625,000 miles per hour. The solar wind creates a bubble in space containing the Sun and planets called the heliosphere. The heliospheric current sheet extends to the outer reaches of the solar system and results from the influence of the Sun's rotating magnetic field on the plasma in the interplanetary medium. Review the following information to learn about the active Sun.
The granules and supergranules and the solar wind occur continuously, but the Sun's atmosphere is periodically disrupted by magnetic fields that stir things up, and this is what we call the active Sun.
Sunspots are the Sun's most obvious transient active features. The surface temperature is approximately 10,000 degrees Fahrenheit, but this cooler sunspot is only about 8,500 degrees Fahrenheit. This temperature difference is what makes a sunspot appear black. Sunspots are regions slightly cooler than the rest of the solar surface and have strong magnetic fields. The magnetic fields in sunspots are about 1,000 times stronger than average. In sunspots, magnetic field lines emerge out of the photosphere. Sunspots come and go in an 11-year cycle. Sunspot activity affects shortwave radio communication, the Earth's magnetic field, and the aurora.
Here we see sunspot minimum on the left and sunspot maximum of the 11-year cycle.
The Sun's magnetic fields create sunspots. In 1908, a spectroscope was focused on sunlight coming from a sunspot. It was observed that an absorption spectral line of the element iron, seen in the normal solar spectrum, was now seen to be flanked by two additional closely spaced spectral lines not usually observed. This splitting of a single spectral line into two or more lines is called the Zeeman effect. The Dutch physicist Peter Zeeman first showed that an intense magnetic field splits the spectral lines of a light source inside the field. The more intense the magnetic field, the more the lines are separated. In this animation, you can adjust the strength of the magnetic field around a star to study the effects on the star's spectrum.
No, you can't. This animation is broken. We're moving on.
Sunspots reveal the Sun's rotation. Galileo observed the phenomenon of solar rotation in the early 1600s by measuring the motion of sunspots across the solar surface. Solar magnetic fields also create the solar atmospheric phenomena known as prominences. These are huge volumes of gas that are lofted upward from the photosphere by the Sun's magnetic field. Active solar prominences are a characteristic of sunspots. Prominences can, however, also be present without sunspots or visibly active regions of the photosphere. The occurrence of solar prominences that happen away from the active regions or sunspots are called quiescent prominences. In this image, the gas in the prominence was so energetic that it broke free from the magnetic fields that shaped and confined it. The size of the Earth is at the top left. Review the following information about the Sun's interior.
Thermonuclear reactions in the core of the Sun is its energy. 99% of all stars are thermonuclear fusing devices. We have burned out stars and other such things, but we'll look at that later. At this point, we only want to understand that what makes stars go is thermonuclear fusion, the fusion of hydrogen and helium, and the resultant release of energy.
Thermonuclear fusion reactions in the core of our Sun convert 4 hydrogen atoms into 1 helium atom. The newly created helium atom has less mass than the 4 hydrogen atoms that created it. This mass being converted to energy via the equation E equals mc squared.
And that is all we have to say about thermonuclear fusion. 4-to-1, that's all you need to know. Forget it, this isn't thermonuclear fusion course.
The core of our Sun, in which all the thermonuclear energy is produced, takes about 1/4 of the Sun's radius. In terms of its total hydrogen burning lifetime, our Sun is about halfway through its life.
Our Sun will burn for another 5 billion years as a bright yellow G2V star, and it will eventually expand to a red giant and then collapse to a white dwarf. We look at this phenomenon in the 3rd section of the course. So in this module, we've learned about the Sun's structure, that we see the photosphere and we look down through the chromosphere and the corona. We've looked at components of the Sun and the fact that thermonuclear fusion of hydrogen and helium is the source of energy for stars.